Okay, so thank you so much. Thank you so much for the invitation. To be here today is a pleasure, not to be only able to be talking about the Euclid mission, that it is one of my biggest passions, but also to be representing the Euclid consortium, but also the ESA Euclid team. So I'm going to be introducing you to the main scientific goals of the mission, the status of the mission, and you can actually find most of the information in this preprint paper. So it is the Euclid Consortium paper 1, the overview of the mission that appeared on the archive a couple of months ago. And only a few days, I think it was 3 days ago, we received a positive referee report that it is going to be accepted to be published in ANA. So really, really excited about that. So you know that we have Euclid pictures. You have probably seen the posters out there. This came from a program that the ESA Euclid team prepared early last year, that it was called the Early Release Observation. So the plan was to give the scientific community the opportunity to tell what were the first science interesting areas of space that Euclid should be taking pictures of. And there were like two concerns. So the main one is that scientifically they had to be interesting, but they also had to have the wow effect. So they had to be like really visually appealing. And this was the first set of pictures that we released last year, so November 2023. Really exciting. I must admit that for me, seeing the Horse Nebula in this super broad field of view was really exciting. And I thought, okay, there is nothing that can be equal to this effect, this wow effect that we had in November. But no, we had it a few months ago, so in May, with the second release of pictures from Euclid. And what it is important is in the last time that we were releasing pictures, it wasn't only anymore about the wow effect. We have actually demonstrated that we can do science with Euclid, so we released this data to the community, so please be my guest, do yourself a favor, go to ESA Sky, see the images in really high resolution, but also download the data, play with it, or at least have a look at the 10 different scientific papers that accompanied the pictures. There were also 5 other papers from the Euclid Consortium, including this overview paper that I'm going to be guiding you through in the next 22 minutes. So let's get started. Euclid is a fantastic piece of engineering. And even though we have demonstrated that we can do the wow effect for legacy science, so we can take very pretty pictures of the universe and we can do science with it, in reality, Euclid has really clear primary scientific goals. And they come from the fact that at least 95% of our universe is completely unknown to us. So we know that 25% of the universe is composed of what we call dark matter, so some type of matter that we know, or we call it matter, because it interacts gravitationally, but not with light. And we know that our universe is expanding in an accelerated way. That is extremely puzzling. If we assume that somehow there is some unknown substance that it is fooling this acceleration, that we denominated dark energy, at least 70% of the composition of the universe should be that dark energy. And that makes up of the fact that we have 95% of the universe that we lack whatsoever some intrinsic understanding about their nature. And this is a failure of what we call our standard cosmological model, or the Lambda-CDM model. So this is what Euclid is trying to solve. So Euclid is going to map, or it is currently mapping, finally, it is a challenge here to not be talking in the future, but in the present. So Euclid is currently mapping the last 2 billion years of cosmic history to create the biggest galaxy catalog of the universe. So basically, we are collecting positions, shapes, and distances of billions of galaxies between redshift 0 up to redshift 3. Why are we doing this? Because Euclid has really clear scientific objectives. So as I said, discern the nature of dark matter and dark energy, but not only qualitatively, okay? So we are aiming to make this in a statistical way. So we are aiming to put a statistical constraint on some of the parameters that might identify the nature of dark matter and dark energy. On top of that, because we know that the large scale structure that we are seeing these days of the universe, so how this late evolution of the universe looks like, has some relation to the primordial density perturbations that we are actually seeing in the cosmic microwave background. We can also indirectly say something about the initial conditions of the universe. On top of that, Euclid has also some requirements on the measure the sum of the neutrino masses. So as you said, really clear scientific goals that are collected in what we call our Euclid Red Book. Who is behind this? Well, the Euclid Consortium partnered, of course, with ESA, is responsible of the scientific exploitation, but also providing the instruments on board. So the instruments that have been operating, that are currently operating in the Euclid spacecraft, were provided by the Euclid Consortium, of course, partnered with ESA and up to some point with NASA. We have more than 2,700 scientists registered. This is what we have in the database. Active scientists is around half, and we are distributed between 14 different countries, actually 15 since really recently, because Hungary has also joined the game, with few scientists from the US, Canada, and Japan. So yeah, we are a big community, and we are interested mostly in dark energy. So this is what we say that Euclid is going to be mapping, or it is going to be discovering the dark side of the universe. Our main focus is dark energy. And we are not envisioned to do something really big or something really challenging, because even the least challenging things are already difficult. So we are focusing in two different approaches. So we know that we have the standard cosmological model, so this lambda CDM model, in which lambda is used to parameterize this accelerated expansion of the universe. If we assume that actually there is some kind of dark energy out there that has some equation of a state, okay, challenge number one. Let's measure that equation of a state that we usually parameterize with the parameters W0 and WA. And this is where we would like to put our statistical constraints. So the goal of the Euclid mission is to measure as well as possible the uncertainty, so the Bayesian statistical uncertainty of the equation of a state of dark energy, so this W0 and WA, with a figure of merit that it is larger than 400. That this number is really important in the Euclid Consortium because this is actually our ultimate goal. With this, we could be saying something about dark energy. There is another possibility, which is that we don't understand gravity at larger scales. So we would like to study a series of modified gravity models, but as I said, challenging, it's a small challenge are already enough challenging. And how are we going to do that? We are using a parameterization of the growth rate using the so-called lambda leader parameter, for which if we measure this parameter with some requirements, that it is also in our Euclid Red Book, we will be able to discern among different modified gravity models. Okay, so now we know that Euclid is mapping our universe, so between redshift 0 and redshift 3, so we are going to have data. We have some challenges of our standard cosmological model. How do we make the combination between the two? You need to somehow compress the information, so this extremely big catalog, to be able to compare with the underlying cosmological model. How do we do that? Euclid has two main primary cosmological probes. The first one, gravitational lensing, and the second, galaxy clustering. Why? Because we cannot measure dark matter and dark energy directly, okay? Every single effect is gonna come in directly from understanding how well matter is clustering and how much matter we have. And of course, as well, by measuring this expansion rate of the universe. So we have two probes that are sensitive to this, as I said. The first is gravitational lensing, and we are not aiming to survey 1/3 of the sky just because 1/3 is not sufficiently challenging. It's because this is a mission about modern cosmology, or precision cosmology, which means a statistical cosmology. We are interested in mapping the overall matter distribution of the universe by means of studying the subtle deviations on the shape of galaxies whose light gets distorted just to the fact that we have matter in between the line of path. Therefore, by measuring at least billions of galaxies, and we are aiming to have at least 2.2 times 10 to the 9 galaxies for which we are going to be measuring their statistical deviation. Using weak lensing, we will have this map of where matter is located in the universe. In reality, Euclid is not starting to do this on its own. Okay? Euclid is what we call a large-scale structure survey stage 4. We are basing our knowledge from stage 3 surveys. So for instance, KISS and DS. And what we have seen is that there is sufficient constraining power in weak lensing, but we increase that if we actually combine the relation between not only the deviation of the shapes of the galaxies, but also studying how is the position of the lenses that are making these shapes to be deviated. So we use in reality for the photometric survey like a combination of what we call the 3 times 2 statistics. So it will be weak lensing, Also, the positions of galaxies when we measure the distances using photometry and the combination between the two. And this is what, colloquially, within the Euclid consortium, we refer to as weak lensing. But please bear in mind that in reality, it's a 3x2 statistics. How are we going to gain? How are we going to do better? How are we already doing better than stage 3 surveys? Well, the reality is that we are measuring way more galaxies. So we are increasing our statistical certainty by increasing the number density of galaxies that we have between redshift 0 and redshift 3. And what it makes is basically to decrease our error bars on the measurements that we have, the predictions of the measurements that we have for the angular power spectra that we are going to use. Okay. But we know that measuring distances to galaxies with photometry is not extremely precise. So this is the reason why Euclid also focused on another probe, that it is galaxy clustering and in particular baryonic acoustic oscillations. So we know that there is a relation between the areas that were more overdense or underdense in the really primordial universe to what we are seeing these days as the large scale structure of the universe. And if we really measure precisely the position of galaxies in the sky, we should be able to see this relation that basically is what we call baryonic acoustic oscillations. In reality, with Euclid, what we are aiming to measure is the full shape galaxy clustering power spectra, so the 3D one, using Legendre multiples. And with this, so you see here the baryonic acoustic oscillations, we should be able to put time constraints on the expansion rate of the universe. Okay, so we have a challenge, which is map 1/3 of the sky, 3D, to constrain dark energy and dark matter. And we have two main primary probes that in principle are sensitive and they are up for this task. Let's see how Euclid was designed for this. So let's talk a little bit about the spacecraft. But first, let me say that Euclid has finally fulfilled his first birthday on space. It's amazing to think that we have already been for 1 year in space, not only collecting data, but facing like different challenges that you're going to be seeing here today. One of the best things of being working currently at the European Space Agency is that I had the opportunity to see the Euclid spacecraft with my own eyes before it was shipped to the US. It's beautiful. It's a very rudimentary telescope, so 1.2 diameter with the sun shield and the payload located here, but it is really powerful and it actually contains the most important piece that we have in the spacecraft, which are the instruments. So remember, we are basically measuring shapes of galaxies and distances to galaxies and their position. So for that, we need to have a really powerful camera that we can use to measure the shape of the galaxies, and we need to have an instrument that would allow us to basically measure distance to galaxies. So this is why Euclid has two instruments on board. First, the visible instrument that takes very high quality images, and then we have our near infrared detectors. This is where we have contributions from NASA that basically we use to obtain photometric but spectroscopic redshifts, so distances to galaxies. And voila, this is how they are located into the payload. Please pay attention a little bit here, otherwise I wouldn't have included because I will give you some piece of information later that it will be on the interest of the community. But basically what you can see is that you have this here is the NISP, and we direct the light all over to one instrument to another by means of using different mirrors or folding mirrors. This is important, and please remember that we have this folding mirror 3 that pass lights to this and to NISP. This is how it looks like. So basically, the FIS instrument, it is an array of 6x6 CCDs, and NISP is 4x4. We are using these two instruments to create this 3D map of the universe between redshift 0 and redshift 3. This is what we call the Euclid-wide survey. The goal is to map 14,000 square degrees of the sky on a mission duration of around 6 years. On the first data release, that it will happen hopefully summer 2026, we are aiming to basically do cosmology with 2,500 square degrees. Right now, we have collected data for around 1,000 square degrees, and if you're interested in seeing how fast we are retrieving data, because Euclid takes 10 square degrees per day, you can actually go to our Euclid Cosmos website at the European Space Agency, so we update that daily. What it is important is that right after the summer, this is my last opportunity to have like some proper holidays, because we are going to have a patch of 500 square degrees fully processed that we are aiming to do cosmology with it. So we are actually getting ourselves busy, but we have already been busy since the beginning of the launch, because of course we have to do performance verification. Well, we have to go through commissioning, performance verification,
And it's widely known that we have some challenges. So first challenge, we turned these on, and voila, we had some light contamination of our CCDs, an annoying straight light. This came as a surprise, a really unpleasant surprise. To be honest, this could have messed up completely the mission, but jointly, ESA and the scientific community managed to reduce this straight light contamination by finding a configuration of the spacecraft for which we could operate, and this straight light that comes from some inner reflection was reduced. So this came with a cost of saving the mission, which means that we have to replan the whole survey, but we did. We did in record time, and we are currently taking care of that survey. That is not enough. So months ago, everyone was super happy because we were seeing northern lights in many parts of Europe that usually we don't get northern lights. And yeah, the community was really excited. The Euclideans were terrified. And this is the reason that we have basically X-ray contamination. So we have X-rays that are filtering through the sun shield, and we are operating in the maximum peak of activity of the sun. So yeah, that has not been the best idea to make, but again, we are up to the challenge. The reality is that we are missing, well, we are basically losing some of the data collection when we have very powerful X-ray flares. There is something else, so ice contamination. We have ice in Euclid. Where is this ice coming from? When the instruments were assembled into the payload, we couldn't reduce completely the water molecules that we had in the payload. We already knew this. We already knew that we could potentially have ice due to the temperature gradients in space, and we had a mechanism in place to reduce this ice. But it is true that it came slightly as a surprise when we started monitoring the magnitude of stars. So here, this is a fantastic example of synergies between two ESA missions, Euclid and Gaia. So we are monitoring how foggy our CCDs are becoming by looking at the magnitude of stars that have been really well measured by Gaia. And what you could see is that since we started monitoring, like in September last year, well, the throughput was more or less staying stable. It went still, there was still above the requirements. There was the decision of actually making the first decontamination campaign to retrieve like some throughput. In a period of 1 month, we saw that that throughput decayed very drastically. We believe that it is due to the crystallization of how the ice was formed. We performed a second decontamination campaign. ESA gave me permission 3 days ago to actually tell you how we are looking like at the moment, and we are fine. So in the last 1 month, we are still maintaining a pretty stable throughput. So what do Euclideans do every morning while they are having coffee? They look at the ice news to see if this data is still worth for the survey. And this has been an extraordinary relief. We are still understanding the behavior, but what it matters is that we have a de-icing decontamination in place that we can perform in a very rudimentary way and in a routine way to maintain our Euclid survey alive. So survey products. We take the survey, and we are collecting the survey, position, shapes, distances. We will produce catalogs to actually calculate two-point statistics, so correlation functions of angular power spectra. This is some predictions of how they look like for shear. And if there is someone in the room, actually I didn't get permission for this because it is still internal, and it might be going through the blinding strategy that we have in the Euclid Consortium for data release 1. But if there is someone here that have Euclid credential and it wasn't in the Rome meeting 2 weeks ago and wants to see the first angular power spectra that we have for photometry, please come to me during the coffee break because I'm willing to show it. What it matters is that the science ground segment of the Euclid Consortium has finally processed end-to-end the pipeline. So it went from pictures up to calculated the angular power spectrum for the photometric probes, and this has been the biggest milestone that we have achieved. Data releases, I have already anticipated. We are doing the first data release summer 2026, up to a completion of the mission 6 years after, in some years from now. So we actually have work to do. Data transfer, Euclid is collecting tons of data. Really tons of data. So we have to be prepared for that. So not only in terms of collection of the data, we are retrieving the data daily. Euclid has a memory on board in case that something goes wrong, we can always retrieve the observations from the previous day. But we had to be up to the challenge to process of the data. So we needed to construct different data centers, which are distributed all around Europe, plus one in the US, that are basically processing this part of the pipeline that I was telling you before. Finally, what do we do? Okay, so we have the survey, we have the data, we have some challenge to the standard cosmological model. We do statistics. This is what we do usually in science, right? So how do we actually perform cosmology with the primary probes? We are following a Bayesian statistical approach in which we have our two-point statistics, so power spectra or correlation functions. We compute the theoretical predictions given an underlying cosmological model. There is a price that you have to pay when you're doing cosmology with large-scale structure and you're not doing cosmology with the cosmic microwave background, and it's the fact that our universe is highly nonlinear. So this is one of the biggest bottlenecks and challenges that we have within the theory science working group of the Euclid Consortium. We need to digest the Euclid data to make the computation of the likelihood or to compare statistically so that we can retrieve the uncertainty of the cosmological parameters, because if you remember, we are interested in the figure of merit for W0 and WA. And this is basically my role within the Euclid Consortium. This is where I operate in the full Euclid Consortium pipeline. So in the Euclid Consortium overview paper, you can see the latest forecast that we have for data release 3 of Euclid, in which we have already demonstrated that we can provide like a figure of merit for these parameters, so W0, WA, when we use the combination of the photometric probes and galaxy clustering probes above 400. So we are up for the task, we are up for the challenge, and we repeated the same exercise as well with this parameter that I was introducing you before, this gamma-Linder parameter, that it should be below 0.2. Below 0.02, and you see that even with the photometric probes, we should be able to say something about modified gravity models. It is true that these forecasts were optimistic, but we can still use higher order statistics from the probes that I was not mentioning here about. So conclusions and outlook. When I was preparing this presentation, it is true that when you're working in a collaboration, you tend to be pessimistic because you only see the problems. But when I was making this overview, I was actually seeing all the problems that we overcame in the last year. And this year has been really fruitful, really exhausting, but we have demonstrated that we are up for the task. So since we launched in last year, July 1st, we have basically been operated from L2. We are collecting the survey. We have identified many problems during performance verification, well, during the commissioning performance verification, and even these days with the eyes. But we have been overcoming these issues still to be focusing on the science, because that's the thing. We need to say something in the duration of 6 years of the mission. We really would like to unveil or say something more about the nature of dark energy and dark matter, at least trying to understand better this accelerated expansion of the universe that we are seeing today. The goal, have a survey of 14,000 square degrees, which is a lot of data to process. And we are going to have the first exercise of having these 500 square degrees right after the summer. This is the first time that we are going to have hands-on experience, so we are going to get our hands dirty to try to process the first data and try to say something cosmology-like. And 500 square degrees, we were doing cosmology 5 years ago with that in stage 3. So this is the power of Euclid. The first data release of Euclid, that it will be like 2,500 square degrees, should be at the level better of the last results that we are still waiting for DS year 6. In any case, if you're not interested in cosmology like me, in the sense that I'm one of the core theoretical cosmologists of the Euclid mission, we have seen it with the early release observation program of Euclid. The potential of Euclid for legacy science is huge. It's really huge. We are mapping, we are seeing some areas of the sky for the very first time, and we will actually be saying that for 14,000 square degrees. So we will have a Q1, so basically legacy science release of data in March next year. So if you're an astrophysicist or an astronomer and you are really waiting for Euclid data, you just need to wait like 9 months from now. And yes, I will stop here just by saying once more, thank you again for the Euclid Consortium for representing them today, and I will take your questions. Thank you so much.
Thank you very much for the lovely talk. Any questions? Yes.
Thank you very much for this very nice talk. So I had a question about the photometric galaxy catalogs that eventually you are going to release. So up to which redshift you are planning to observe, and what is the level of completeness of these catalogs that you think you might have?
What do you mean by completeness? Is we are using also redshifts from other missions to complement the survey, or?
Yes, for instance.
Okay, fair enough. Let me just look. I have the N of zeta, so the galaxy density distribution. Where are you? Here you are. Yeah. So it is for the photometric survey. So we are going up to, from redshift 0 up to redshift 3. So this black line that you see here is basically the convolution of the different galaxy redshift distribution that we are going to be using. So if you go into the overview paper, you will actually see that we are aiming for data release 3 to use 13 redshifts bins, so basically going from 0, or like it has D offset of 0.0 something. We are using combinations from DS for the photometric redshifts in the south hemisphere. We are aiming to actually use as well LSST redshifts for data release 3, but there is like a long time for that. So for data release 1, you should be able, this is information that I cannot share because this is still internal to the Euclid consortium, but you should be aiming something slightly better than DS-ER6. So have a look at the paper of DS-ER6 whenever they are doing it, and yeah, a factor of, multiply that by 1.3 or 1.4 in terms of the gains in the redshift distribution that we will have with Euclid. Does that answer your question?
Yeah, okay. Thank you.
Yes, Kelly?
Thank you so much. I was just wondering if, with the enormous data volumes, are you concerned, or has there been pressure with space communications?
Yeah, so, well, this is something in which the homework was really nicely done way before the launch, even during the time that the Euclid Red Book was being written. Well, communication on different levels. So first of all, the antennas that we are using to retrieve the information daily, they had to be updated, and actually one had to be built to be able to collect the data. Euclid is the first mission that actually operates with the kind of memory on board that it has. So Euclid had to come up with a very challenging requirements for the weight that we have for the spacecraft, so including a hard disk to be able to maintain the data. Maybe wasn't the best option, yet it was done an exercise to actually keep it as a backup, because losing 1 day of data is losing a lot of data. And finally, the communications is, so we retrieve it from the operation control in Darmstadt, so that they retrieve the basic metadata, so on and so forth. The scientific data is transferred to ISAC in Madrid, and then they are communicated to all these different data centers that we have in Europe, and they basically do some part of the pipeline. Some of these data centers were already there. Most of them had to be updated, and some of them were built precisely for this. So the one that we have in Groningen in the Netherlands was particularly built for doing this merging of the photo-Cs with other missions. But yeah, it was a huge challenge, but so far it's working, which I'm really happy, because having things that work, you know about it. It's definitely a challenge, but yeah, it's doing fine. It's actually doing fine.
NASA's just having a lot of concerns about space communications, like the DSN and the near-Earth sort of satellite systems. So it's good to hear that example of something working out.
I didn't realize, actually, I was also always giving it for granted. I come from the last part of the pipeline, so more theoretical cosmology, so I've been learning more about how the science operates since I joined ESA. And when I discovered how it works, I was like, wow, voila, fantastic. Well done, guys, well done. Any other question about Euclid? Take advantage that we are going to be busy in September, so.
We may have time for one very quick question.
Yeah, sorry. So I was thinking about maybe, do you have any plan on working in synergy with gravitational wave observatories?
Yeah, so I didn't have time to go through it really quickly, last 10 seconds. So the Euclid consortium is basically divided between the science ground segment and science working groups. Within the theory science working group, there is a special working package, which is synergy with other probes, so that is cross-correlation with gravitational waves. Yeah. I participate in that. It is true that for the moment it has been
a little bit inactive, basically because we have some other constraints and some other more urgent problems to look like. But it is starting to become slightly active again in collaboration with galaxy clustering. So if there is someone who is aiming to do some cosmology, so cross-correlation of the stochastic gravitational wave background, or maybe resolve sources, to increase some statistical certainty, for instance, when you cross-correlate with galaxy clustering, just come with me, talk to me during the coffee break, and I can point you maybe to some key players. Because, yeah, for me, it will be mostly doing lambda CDM with Euclid in September.
Thanks.
Okay, so I think...
Let's thank Guada once again.
Thank you so much, guys.